Let me begin by saying that chapter 8 is entirely an abstract chapter. However, the skills here, they're relevant, and I'll show you some examples even from the exam that we just had, where you could apply some of this stuff. If any of you go on to do calculus, then again, this becomes a big part. We'll also apply this stuff in chapter 9, when we look at fractions in algebra. Now, in chapter 8, there are these main objectives. You'll see this word show up over and over again. Factor, factor, factor. And all of these different points here, the first 5 points here, they're listing different ways of factoring. How many of you remember factoring? Or know what the word factoring means in this context? Kind of? Sort of? Okay, all right. More on that very soon. And it might take us a couple of days to go through this properly. Now that we've had our first exam, I've got a better sense of how everyone is doing. So I'll try to slow down in certain places and speed up in others, based on what I've seen so far. And we have 6 sections to cover in this chapter, 8.1 all the way to 8.6. Do any of these things seem familiar? Any of those words?
Yes.
Yes? Okay. So these are all essentially different kinds of factoring techniques or factoring situations that you could apply either on their own or in combination to simplify expressions. So let me really quickly do a quick introduction. Factoring, using an example I said. So let's say you have, we know 3 multiplied by 2 is 6. Right? So when you go this way, you are multiplying. But if you start at 6 over here, and if you go this way, if you take the product and if you break it down into, let's say, its individual components, then what you're doing is factoring. Okay, these components are called factors. So you could say 3 and 2 are factors of 6. Now, this is not the kind of factoring, well, this is not the main kind of factoring we'll be doing. We'll be doing factoring that's applicable to algebra. So we have not just numbers like 3, 2, and 6. We'll have letters and expressions. But does that help everyone see what factoring is? Right? It's essentially a process that allows you to break down a product, so the end result, into its, let's say, smaller components that multiply to give you the end result. Okay, so it's going backwards. That's what the first point here mentions. It's a process that splits a number into its components. It's useful in simplifying algebraic expressions. It's useful in simplifying algebraic fractions. So this is something we'll be doing in chapter 9, right after. And it's useful in solving equations, amongst other things. I kind of talked about the relationship with multiplication. It just goes the other way. Let me show you something from the exam that's relevant to this idea of factoring. Some of you, because there were 2 versions, some of you had a question where you had a cylinder. So this is one example I can think of. You had an example where you had a cylinder and you were asked to find its total surface area. Remember that? Some of you got that right, which was good. Let me really quickly go through this. The total surface area of this 3D shape would be the area of all of its surfaces added together. How many surfaces would you say a cylinder like this has? 3, yeah. The first shape would be this one. The second one would be that circle at the bottom. And the third one would be the, let's say, the body. Does that make sense? Okay, so if the question said lateral surface area, then it would be just the area of the body, not the top and the bottom. But the question said total surface area. Now, I'm going to give you, or at least in terms of the formula sheets, you were given that area of the body would be, so which is LSA, the lateral surface area, is it's 2 pi r h, where h is the height of the cylinder, and 2 pi r is the circumference of the base or the top. What would you say would be the area of the green and the red parts? Will they be the same areas in this case? Yes. We're saying that this cylinder is a right cylinder in the sense that it's not slanting. The sides don't slant inwards or outwards. It's going perfectly straight up. So the area of the red circle, which is the bottom, and the area of the green circle would be the same. So area of the top would be, what formula would you use here? Does anyone remember? For a circle? Yeah, pi and r and, I think you said it, squared, great. And even for the bottom, we have pi r squared. So here's where factoring becomes useful. Would you first of all agree that the total surface area would be the sum of all of these areas? Let's call it TSA, or total surface area. It's going to be the sum of the 2 pi r h plus the pi r squared plus the pi r squared. So factoring becomes useful in making the next bit of calculation easier, more convenient, faster. Can you first of all use any algebraic skills to combine anything here? What can we combine here? The pi r squares. Okay, this one and this one, they are like terms. So when you combine them, you'll get, what do you get? So 2 pi r h is the first one. Let me just start with that. It didn't change. But someone give me an answer for this one. What did you say?
Was it pi squared r to the 4th?
No. It's like adding x and x.
Yeah,
So it's like adding x plus x. You'll get,
pi r squared.
yeah. X plus x is 2x, so pi r squared plus pi r squared would be 2 pi r squared. Still with me here? We haven't done any factoring yet. But imagine if you had to calculate the total surface area. You have two options, broadly speaking. You could find the area of the body using this formula. You could find the area of the top and the bottom using these formulas, and then add them, right? But those are three different computations, three different calculations. If you, before you actually evaluate, before you calculate, if you do a little bit of, let's say, rejigging of the actual formula, you can make your final calculation a lot easier. First thing we did was we combined these two to get this term. Everyone still okay? And there's one specific factoring technique you can apply here. It's the most basic kind of factoring technique. It's called common factoring, which is what we'll get up to. So this is a nice, let's say, segue into that topic. Common factoring essentially means you have to pull out the most you can from however many terms you see. How many terms do you see here? 2 terms? 3 terms? More? 2. Terms are just parts of an expression separated by plus or minus sign. So this is 1 term. So that's your first term, and this is your second term. Now, in each of these terms, do you see something that's common to both? What can I pull out from each of them? There's a 2 and a pi. Okay, so I can pull out 2 and pi. What else is common to both?
R.
1 r at least. Okay. And so if you pull out 2 pi and r from each of them, what's left over in the first term?
1 plus r.
No, there's an h left. And in the second one, there's an r. And that's it. This is as much as you can, let's say, factor in this case. But what this does is when you finally put in your values of h and r, here, here, and here, your overall, the number of calculations or computations you'd have to do becomes a lot easier. And that's one, let's say, one thing you can do with factoring. Make your overall calculation easier. This, of course, made more sense when there were no calculators. But even now, you can make your calculations a lot simpler like this. So we just created a formula for total surface area of a cylinder. Okay, anyway, that was a nice little segue into the idea of common factoring, which is the first topic here. And when it comes to factoring, if you're not sure where to start, I would say always try common factoring first. And by try, I mean see if it even applies to a situation. Common factoring is what we just tried in the example I just showed you. But let me take up another example. If you would like to, by the way, get ahead of me, there is a little worksheet posted on Blackboard. You could pull it up on your phones and try to get ahead of me. But let's go through each of these examples. I'll walk you through some of them, but the rest of them you can try on your own, and then you'll get the hang of it. Notice in the actual question, it doesn't give you any hints. It just says factor. Sure, the slide gives you a hint. We're talking about common factors, but the overall, let's say, end goal is if you're given an expression and you need to factor, you'd have to think about what technique you could apply. And what I'm saying is common factoring is the first one you should try to apply. So how many terms do you see here? Everyone sees 3, right? Great. And if we were to talk about common factoring, if we were to try common factoring, can everyone see what's common to each of those terms? Are any numbers common to them? No? But the variable, there are some common elements there. You're right. So what's the most I can pull out in terms of x's?
X.
Just an x. Okay. So I can pull out an x. In other words, when you're looking at variables, you can only pull out the one with the smallest exponent. This x has an exponent of 3. This one has an exponent of 4. The exponent for this x is a 1. And you can only pull out the one with the smallest one. So just decide and be sure of what's left inside. And we'll just conclude with something very soon. And you can try the next few examples. What do you think is left inside? Anyone? Go for it.
3x squared
Okay.
minus 2
Okay.
plus 5x.
Great. And the thing is, even if you're not sure about what you, let's say, write down on the inside, you should, or I would always recommend doing a quick visual or mental check. Here's what you do. Just really quickly multiply x with 3x squared. Do you get the first term? Right? And then x times the negative 2 should give you the second term, and x times that should give you the third term. So always with common factoring, it's really, really good to do that quick visual check right after. And at least in this case, this is the final answer. Can't be factored anymore, any further. Not without making it more complicated. Questions? I have 2 examples, I think, for you to try. Or actually, no, more. 3 examples. 2 examples. That's right. Here is the first one. Just try this one and the next one, and we'll move on to the next factoring technique. You would do this. You were able to pull out 3x and y, right?
Yeah.
In the next step, what happens is you would need to put brackets with a lot of space. And I don't know if you noticed in the previous example, but I'll make this more clear here. In the original expression, there were 3 terms, and could you have added them or subtracted them further? Were they like terms? No, you're right. So when you apply common factoring to this kind of a situation, inside the bracket you should still expect 3 terms. 3 terms. So let's look at what the first term would be if you were to pull out a 3 and an x and a y. Michael, what are you leaning towards? What do you think might be left?
For the first one,
Yeah,
y.
just y, you're right.
Yeah.
And a quick visual check confirms it. 3xy times y should be 3xy squared. The second term would be 3x squared, okay? And the last one would be 2 and... Sorry, that's it. So in this case, that's as much as we can do. Does that make sense for everyone? All right, let's keep going. Final example from this section, we can move on. Are you getting that answer? Remember, common factoring, it's the most basic technique for factoring, and it's what I would recommend that you could try to apply if you're not sure of what to do in a factoring situation. Can we move on to the next one? Okay. The next one is called difference of squares, specifically difference of two squares. And you might remember this. It looks like this. I'll write it out better. It's pixelated. A squared minus b squared. If you have an expression that looks like a difference, literally a difference of two things that are perfect squares, you could factor this out into the sum of those two things and the difference of those two things. So the main thing in trying to apply difference of squares to factor is you have to try to, we'll take up an example or a few examples very soon. You'll have to try to see if you could figure out what the A and B are for each situation. So an example like this, for instance. Now pretend you didn't have this heading at all. And the question just said factor the following expression, and you weren't entirely sure what to do. Let's try common factoring. Do you think we can apply common factoring here? Is there anything common to these two terms? No, right. So common factoring doesn't work. But what you should notice is that there are two terms, and difference of two squares is something you can apply to expressions having two terms, as long as there is a way to express this. Can you rewrite that as something squared? And can you rewrite this as something else squared? If the answer is yes, then you can use difference of squares. So what needs to go in the blue bracket? What would you say? Go for it, Derek. Yep, it is. And that's because 2 squared becomes 4, x squared becomes that. What about in the red bracket? Maybe I can answer this question on my own. 3. But again, I want you to be able to do this there are more examples for you to try very soon. As long as you're able to do this, then this thing here is essentially A. This whole thing inside the bracket is A, and this whole thing inside the bracket is B. And remember what the formula or the identity says: A squared minus B squared equals A plus B times A minus B. So it's really crucial that you identify A and B correctly, because the next step would be 2 brackets, and A is 2x, B is 3, so it's 2x plus 3, and then 2x minus 3. So once again, we were able to break down this expression into a product of two things, and that's us achieving factoring. So here is the next example. See if you can factor this one out correctly. Here's another one. keep this one in mind. Difference of squares in general. I mean, it's going to make a reappearance very soon in a trick question that we will encounter soon.
Is this the trick question?
No, not this one. No. So again, even here, as long as you notice that there is a subtraction between two terms, and there's a way to write each of those terms like this, as a square of something. Can everyone see what needs to go in the first and the second brackets? Like really quickly, in the first bracket, what would you put?
3A.
3A, perfect. And the second one, there would be a 4B. So as long as you can do this, you can use the difference of square formula, which allows you to create two brackets. Think of this one here as A, this is B, and the formula is A squared minus B squared equals A plus B times A minus B. So as long as you can see this in a situation, you can create the factored form. So, still kind of straightforward, would you say? Maybe I'll skip the next example. Can you at least visually see how you would factor this one?
No.
I don't know if you're joking or not, but okay, I'll do one step. Is it possible to, well, we do notice there are two terms and there's a subtraction between them. Can we rewrite this as something squared minus something squared?
ABC.
1, and in the second bracket you said ABC? Yeah, you're right. Because ABC squared would become that. And as long as you can do this, you've got your answer. You can set up your answer, using the two brackets. This first thing is your A, the second thing is your B. I said I'd skip this one, but here I am, and we went through it. Here we are. So imagine, this is a good question. What if you had a question like this? Factor -1 and then plus A squared plus B squared plus C squared. What would you do here? Remember, difference of squares is something you can apply if there are two terms in subtraction. Hey, Andrew, go for it.
You wanted to know whether the equation correct?
You're talking about this made-up example over there?
Oh wait, no, it's
It's a made-up example. Say that again? Yeah. So the thing is, at the moment you have this term that's negative and this term that's positive. You could rearrange them to get this, to say that this is the same thing as A squared, B squared, C squared minus A1. In other words, there's still a difference between two terms. And then the question becomes, can we write it like this? If the answer is yes, which it is in this case, you can write this as ABC and this one is just a 1. You can again use difference of squares. If they are both negative, then it can be an issue. Yeah. But as long as one of them is negative and you can express both of them like this, you can use difference of squares. You'd get ABC plus 1 and ABC. All right, third factoring technique. This might, actually wait, hold on. There's another example that we should probably look at. Let's do a quick visual inspection. If you were to see something like this, what would you do here? Can we still use difference of squares? Is it already set up for us nicely? So there's a subtraction sign, and you could write this thing here as x squared. But if you take a look at the second bracket, in a way it's already set up as square of something. I know that something is an a plus b, but it is set up as a square of something. So technically, this whole thing here you could call a, this whole thing here you could call b, And once again, use a squared minus b squared equals. It's a lot like puzzle solving, I guess, and seeing certain patterns. But this example, even though you may have not seen it in the beginning, it's nicely set up for us to use difference of squares to factor. And you would eventually get a was a plus b, and that a plus b minus x. That would be the answer here. All right, so specifically keep this example in mind for the trick question, as I call it. Keep going. All right. You know what? I should come back. No, let's do this now. Final example in this topic. Again, all of these questions will have pretty much the same instruction, which is to factor. Let's take a look at what let's take a look at what we're dealing with. We have two terms, and there's subtraction going on between them. So maybe difference of squares can be applied. Maybe. Is it possible for us to write this as a square of something? Squares being subtracted. Yes, no? Most of you are saying no. Okay, so the real technical answer is yes, but it's more complicated. We won't go there. Instead, if you're saying that we cannot write them as perfect squares, which is what we'll focus on, is there some other factoring technique we could apply before we use difference of squares? Common factoring, right? They both have a common to them. So let's see what we get when you pull out the a's from each. If I pull out a from each of them, what's left inside? One minus, yeah. So we had two terms in the beginning. You would still be left with two terms inside the bracket. So 1 minus b squared. Remember to check a times 1 should be a, and a times this should be the second term. Is that first step okay? So this example is a good way of showing how you cannot just use difference of squares right off the start. Sometimes you have to use other techniques to...
What's like the square root of a, though? Not b?
Which is why I said the other way of doing it would result in something that doesn't look nice, but it is technically possible. Yeah, I could show it to you very soon, but for now at least, we can stick to, let's say, the cleaner versions. Is that the factored form then of the expression, or can we do more? Zach? Yeah, we can factor this expression even more, because this is where difference of squares really kicks in, at least in that example. So the a is still by itself, and the more you do this, the more quickly you'll be able to just create the factored form. What do you think is going to be a here, and what's going to be b here? Andre, what do you think?
A, 1 minus b, and then, 1 plus b, and then 1 minus b.
Oh, you're talking about the two brackets. Okay, all right. I'll take that. 1 plus b and 1 minus b. Great. In other words, the a in this case is 1, and b is, well, b. And that would be the factored form for that example. So there can be layers, essentially. You may have to try different techniques to get to the most factored form for any expression. Questions about this example? Anything at all? Next technique, factoring quadratic trinomials. So there are a few words here that we should really quickly go over. How many of you know what trinomials, what that word means? Three terms. Okay, so a three-term expression. So an algebraic expression that contains three terms, in addition or subtraction, doesn't matter. And then there's another word, quadratic. So quadratic would mean so we're going to specifically look at how to factor three-termed expressions where the highest exponent on the variables is a 2, aka quadratic trinomials. You've seen them obviously before a lot. These are both examples of quadratic expressions. They're not equations because they're not set equal to anything. They're just expressions. And we'll specifically look at how to factor these expressions. This one. And at least in this particular section, we're going to look at how to factor expressions that look like this as opposed to this. Do you notice the main difference between these two expressions?
Simple. One's I can't remember the other name. It was simple
and so what makes you call this one the simpler case, and what makes you call this one, let's say, not simple?
You have to do a different step for the second one. You have to multiply C by the coefficient of A,
Mm-hmm.
and then you do that table. I can't remember what it's called though.
Okay, all right. So let me jump in
But I do know
with a few things here. In this section, we'll deal with these expressions, and the main difference between this expression and that expression is that the coefficient, the number in front of x squared here, is a 1. Right? So right now there's a 1 over here, but in this expression it's a 3. So any expression that has a 1 in front of x squared, any of these expressions that have 1 up here, they are really easy to factor compared to this one. More steps, as you said, involved here. Fewer steps involved here. And right now, we'll just focus on this. Let's use an example. So you might hear me say this, leading coefficient of 1, which again just means that first number with the x squared term is 1. But let's look at some examples to get the hang of this. Some of you might already know what needs to be done. How many of you know, by the way? Just a quick show of hands. 1, 2, okay, maybe 3. Something that's useful to know. Let me talk about this in a way that also helps us in the long run with expressions that have other numbers here. Okay, so one thing you should do with quadratic expressions like this is identify A and B and C. A is, so in other words, just compare this with, compare x squared plus 6x plus 8 with ax squared plus bx plus c. Essentially, that's what I'm asking you to do. Again, when you know what you're doing, you'll be able to do this in seconds. So, what is a in the given expression?
1.
1. A, remember, is the number in front of x squared. A is definitely 1. What about b?
6.
6, positive 6, and c is an 8. Do you all agree? Great. So I'm looking at the numbers here, here, and here. If there was a negative sign here, b would be negative 6. If there was a negative sign here, b would be c would be negative 8, etc. Second step is to do this. So we have x squared plus 6x plus 8. You're looking for two integers, so by integers I mean positive or negative whole numbers, they should have a product of A times C and a sum of B. So when I say product of A times C, what is the product going to be for this expression? 8. A was 1, C is 8, so 1 times 8 would be just an 8, you're right. And the sum of which is B equals positive 6. So can you think of two integers which when you multiply give you positive 8 and when you add them you get 6? Think about it on your own first. If you can think of those two, then you are that much closer to the answer, to the end of this, well, yeah, the factored form.
It's add to 6, multiply to 8, right?
No, it's oh yeah, sorry. Multiply to 8, add to 6, that's right. I tend to focus on the product first.
It is.
Oh, really?
Hey.
It's 4 2.
4 and 2. Let's check. 4 times 2 is 8. 4 plus 2 makes sense. Sure, of course. Yeah. But for those of you who may not see it immediately, what I'd recommend, and it's just how I like to do it, I tend to focus on the product first. So in the beginning, if you look at the product, notice that it's not negative, it's positive. So if you have a positive product and you're looking for two numbers, I'll just mention look for two numbers whose product 6 and sum is, product is 8 and sum is 6. So if your product is positive, what does that tell you about the two numbers you're looking for?
They're both going to be positive.
They're either both positive or they're both
But
negative,
the other one's
right?
positive as well.
But in this case, because the sum is also positive, can those two numbers be negative?
No.
No, they both have to be positive. So product is 8, sum is 6. As Andre as Andre said before he left, the two numbers that work here are 4 and 2. 4 times 2 is 8. 4 plus 2 is 6. Is that part okay so far? We'll have some more examples to go over to practice this part. But as soon as you are completely confident on the two chosen numbers, and as long as the number here is a 1, you can directly go into factored form like this. You could set up two brackets. Each of them would have x or whatever variable you had in the expression. And then the numbers that you fill in here are the two numbers you chose. So they're both positive, so you could say plus 4 and plus 2. Or you could say plus 2 and plus 4. Doesn't matter. The order doesn't matter. What matters are those two numbers that you have to choose carefully. And this would be the factored form. The long way of checking if this is true or not is to FOIL this out. If you were to multiply this bracket with that bracket, eventually you would get this expression. Okay, so we're just going the opposite way. We're starting with the product and we're breaking it down into its components. Does that make sense? The overall idea? Let's do an example. Let's do another example. Let's try this one. I'll let you try it all the way to the end. This particular kind of factoring, this one in particular is useful when solving quadratic equations. Some of them, you can't solve all of them like that. But so product here would be A times C again. Sum is going to be B. A here is 1, B is negative 6, C is 8. Can everyone see which two numbers work here? Yes. Product is positive, but sum is negative. So negative 2 and negative 4. Always check. Negative 2 times negative 4, positive 8. But negative 2 minus 4, negative 6. It works. So this is good. And because the value of, or the number in front of x squared is exactly 1, you can really quickly just go into your factored form, put x in each of them, and then use these two numbers to fill in the missing stuff. Oops, -4. That would be the answer. Okay, all right. Now remember, this is factoring quadratic trinomials where there's a 1 in the front. It's shorter, it's quicker, as long as you're able to think of these two numbers. 2 sections from now. So in 8.5, we look at how to factor the remaining kinds of quadratic trinomials, when you could have had a 2 here, or a 3, or a 5, or any number over here. Before we get into that kind of factoring, we have to talk about factoring by grouping. And we'll take a few examples to talk about this. Now, factoring by grouping itself actually uses common factoring as its main, let's say, as the main way of getting the job done. At the moment, in this expression, for instance, we have 4 terms. And what the grouping technique really advises is try grouping 2 terms at a time, or sometimes 3 terms at a time, to see if you could factor something common out. What I recommend is if you try this technique, don't begin with grouping 3 things. Just begin by grouping 2 things at a time. It doesn't matter which 2, but let's try the first 2. Let's try the last 2. There is an element of trial and error. Based on how it's set up, I'm going to try the first 2 and the last 2. Is there something that's common in the first 2? What's the most you can take out from the first 2? A, great. So A, and then what's left inside? B and... And what's between them? What sign would you put? +4. Okay, B + 4. Let's check. A times B would be AB, and A times the +4 would be that. Looks good. Let's do the same thing with the last 2. What's the most you can take out from each of them?
You can take out a 3.
Yeah, you can take out a 3. Positive or negative? Positive. So the thing is, if you just write 3 and then bracket B + 4, let's say, you're making a mistake here. Can anyone spot the mistake currently? Derek?
It's still addition.
Right. I did it this way because I've noticed this as a common mistake previously. The actual factoring itself is correct, but if you don't state the sign here, then it's incorrect. Right now, it looks like this is being multiplied with that, but that's not true. There's actually a +3. In other words, you're between these 2, you were able to take out +3. And do you agree we get B + 4 also?
As you say that, I get a text from.
Everyone okay with that step so far? In terms of what we could pull out from the first and the last 2? Okay, what do you think we can do next? How many of you can see right away what needs to be done? Okay, at least 2 people. Andre, I'll try you again. What?
Try. The final thing would be B + 4 and then A + 3.
Okay.
If you take the 2 sides that are multiplied and because these 3 are the same.
Okay, all right. So let me expand on what you just said. You're right, completely. How many can everyone else see what needs to be done too? If you're not sure, let me pose a question like this. In the beginning, with this original expression, how many terms did you see? 4. Everyone is super clear on that. But how many terms do you see here?
3.
No. How many terms do you see at this stage? 2. Exactly. This is 1 term, and this is the second term. And that's because A and the B plus 4, they're sort of stuck together. They're multiplied together. 3 and the B plus 4 also stuck together. Now, between these two terms, do they have something in common?
Yes. B plus 4.
The B plus 4. Because they both have B plus 4 common to them, you can pull out B plus 4. You can pull out B plus 4 from each of them. So B plus 4 taken out from each of them leaves us with A and the 3. A plus 3. And that would be the final answer. So factoring by grouping uses common factoring, essentially. Most of the time. Not always, but most of the time. Is that okay? Right. Here's one for you to try. Let me just check. Okay, yeah. And then there is the trick question, which we'll end with. So trick question coming up soon.
Can we just nod?
So
You got no blue eyes.
here is the creme de la creme in terms of.
Is this the trick, sir?
I remember I reworded it. No longer the trick question, just a challenging
It's
question.
an extremely challenging, unexpected question.
Yeah, let's go with that. The hint is factor by grouping, but let's see if you can figure this one out.